We begin this class. Very good day to everybody. This is algorithms 1, and this is our final topic, which is nothing but the greedy technique, container loading algorithm, and of course the Prim's algorithm. So this is especially for you, my dear students and young researchers, and you can reach me at dr.christoananth@gmail.com. So before beginning the session, once again let me thank God for giving me this opportunity to deliver this useful session to share my knowledge among my fellow national, international participants, students and young researchers. Right. So in this class we discuss about the number of containers that can be filled in the given time, so that we will be using the greedy approach. Then we will have a Python 3 program especially for the implementation. Then we discuss about Prim's algorithm. What are the steps to find the minimum spanning tree using the Prim's algorithm? How we will go with the input graph calculation, and of course the coding implementation of the Prim's algorithm. So at regular intervals, I'll be giving you some short videos to discuss the knowledge in our topics. Right. So here we will be having a number n and maybe a time which is nothing but x unit. The task is to find the number of containers that are completely filled in the x unit if the containers are arranged in a pyramid fashion. Okay, so here we will be having a pyramid arrangement, okay, for n equal to 3. Here n denotes the number of levels in the pyramid shape arrangement of the containers, which has the level of one container. Maybe level 2 has 2 containers, or maybe level 3 has 3 containers. Up to level n we will have n containers. So the liquid, maybe it is poured on the topmost container at the first level. Okay, when the container of one level overflows from both the sides, the container of the lower levels will be filled. Okay, so here the amount of the liquid which is poured in each second would be equal to the volume of the container. Okay, so here this is what I was talking about. So the number of containers that can be filled at any time. So the first level, if it is filled, means immediately equally it will overflow in the second level, and afterwards after filling, equally it will be overflowing in the third level. Right. So here we will be having the input n is equal to 3 and x is equal to 5. Okay. So here if you can see 1, 2, 3, we will be having, okay, the value. Okay. So you can say that the output, it will be just the intermediate value with the case of the n as well as x.
It's like true for bottom half, and it's both, that means.
No, first will have 1, second level will have 2,
Yes.
third level will have
And
3.
for example, when we put the button in the half, it's full and
Overflow.
That's it. When we close the close cap and it's full second, yes?
Equally. Right. But also, like the spacing is also important. Spacing is also important. So if you keep the middle level, maybe this side or that side, it will not exactly overflow in the correct level. Right. So after 1 second, the container at the level 1 will be fully filled. Okay. After 2 seconds, the 2 containers at the level 2 would be half filled. After 3 seconds, the 2 containers at the level 2 would be fully filled. If you can see, 1 second fully filled, after 3 seconds fully filled. Okay. 4th second, out of 3 containers at level 3, 2 containers are quarter filled, and container at the center would be half filled. And after 5 seconds, so 1, 3, 5. Okay, the 2 containers are half filled and container at the center would be fully filled. So since why the center is fully filled means since it is getting from this side and that side. But in the end, you will get only one.
Yes.
Only one. Okay, so that is the reason.
The 5 seconds of this container will
Mm-hmm. So input n is equal to 4 and x is equal to 8, the output would be 6. Okay. So here you can solve it using the greedy approach, where you have the container to be fully filled, and of course the liquid overflows equally from both sides of the container and will be filling the container below it. Okay, so that's a pyramid of containers. That's a matrix. Okay, so here we will be having the container of ij. Okay, that's a liquid of the jth container of the ith row. Okay, so when the overflow occurs, the liquid overflows to container of I plus 1 j and container I plus 1 and j plus 1. Okay, so that's how the liquid will be poured for x number of seconds, and the total amount of liquid poured is x unit. Okay, so the maximum value that can be poured into the container can be x units, and maximum value that can be poured to completely fill is actually 1 unit. Okay. So when the liquid is actually poured into the topmost container, okay, the topmost container will be having the maximum value, which is nothing but x unit. Okay. So you start from the outer loop where like 1 to n for n containers at each level, and inside this loop you start another loop, okay, 1 to I, that's in each container of the each row. Okay. Then you declare a counter, count is equal to 0 for counting the containers which are actually filled. Okay. And if this count container of ij is greater than or equal to 1, okay, then count will be incremented by 1, and of course container of I plus 1 j and g of I plus 1 j plus 1, okay, the liquid will be actually poured, and of course the value will be increased by the value of g of I j minus 1 divided by 2. So that's how the liquid is actually divided into half in both of them. So this is the Python program. Okay, so Python program will have the matrix of containers. So container 0 for j in the range 1000 and for j in the range 1000 even. Okay, so we will have the function to find the number of containers that will be actually filled in x seconds. Okay, so we define the number of containers n and then x. So count is equal to 0. Okay, so container 1 1 that's in the first level. Okay, that's equal to x. So for I in the range 1 comma n plus 1. Okay, so then within the inner loop you will have for j in the range 1 comma I plus 1 plus I. Okay, so that is how you will we earlier started off this one. Okay, if the container gets full, okay, so if container of ij is greater than or equal to 1, okay, so count you are going to increment. So count plus is equal to I. So you divide the liquid equally into two halves. Okay, so container I plus 1j plus equal to container I j minus 1 divided by 2 and container I plus 1 j plus 1 plus equal to container I j minus 1 by 2. Okay, so this is how you try to print the count. Okay, so for the n of 3 and x is equal to 5, the number of containers would be actually filled. Nx we already calculated, that's 4. Okay, so that's the time complexity order of n square, and of course the auxiliary space complexity same order of n square. Right. So this is Prim's algorithm. You find the weighting factors corresponding to each of the nodes. Okay, so that's how you start with a single node, and maybe you will move with the several adjacent node. So what node you have already selected, the minimum you have already selected, that you can put it in the subset. Okay, and afterwards the remaining the adjacent nodes will be selected. That you are going to explore the connected edges. So we start with the empty spanning tree, and you have to maintain the set of vertices that are included. Okay. So the first set will be containing the vertices already included in the minimum spanning tree, and other set which contains the vertices not actually included. Okay. So every step will be containing the edges. Okay, and you will be picking the minimum weighting edge. Okay. So after picking, it moves to the adjacent subsets. Okay. So that's how you are going to connect the two sets of vertices in a graph, that you can call it as a cut in a graph theory. Okay, so for every step you have to find the cut, okay, in the minimum spanning tree, pick the minimum weight, okay, and include the vertices to the minimum spanning tree set even. Okay, so the idea is that the spanning tree, okay, which means that all of the vertices should be connected. Okay, so maybe like two disjoint subsets even can be connected using this spanning tree even, and you have to find the minimum weighting edge. So that is the reason you call it as the minimum spanning tree. So this is the step. Okay, so first of all, create a step minimum spanning tree set, MST set, that is going to keep track about the vertices already included in the minimum spanning tree, and you have to assign a key value. Okay, then initialize all the other key values to infinite. Okay, and first of all you assign the key value as 0, like the first vertex that is to be picked. Okay, so if it doesn't include all the vertices, then you try to pick another vertex, okay, u, which is not there in the minimum spanning tree set even, and that has a minimum key value. Okay, and you try to include u in the MST set. First of all you included first vertices, then you include u in the MST set, and you try to update the key value, especially for the adjacent vertices. Okay, and in order to update the key values, then you try to iterate all the adjacent vertices. Okay, so for every adjacent vertices, if the edge, maybe first you included u, then you included v, so if the weight of uv is lesser than the previous value of b, then you try to update the key value. So with the help of the example, you will try to understand better. Okay, so this is the thing. Okay, so how to find the minimum weightage from the cut event. So here we are including the set of vertices included in the MS tree. Okay, so this is the connected graph. Okay, so there will be weights corresponding. For example, 0 to 1 will have 4, 1 to 2 will have 8. So everything we have the factors. Okay, so first we'll start off with 0. Okay, this 0. Okay, so 0 1 7, 0 1 7. Okay, so first of all, this is assigned. Okay, the set minimum spanning tree will have 0, and all others, as I told you, it will be infinite. So INF means infinite. Okay, you try to pick the vertex with the minimum key value. So here if you can see 0 1 7 0, so vertex 0 is actually picked and it will be included in the MST set event. Okay, so MST set becomes 0. So now it becomes 0. This pink color or maybe rose color, it will be changed into green color. Okay, after including in the set, try to update the key values of the adjacent vertices. So here if you can see, okay, the adjacent vertices for 0, okay, it is 1 and then 7. Okay, so this one you are going to update. Okay, so from here, okay, from 4 it will go to here, this it will go to here. Okay, so this will become 4 and then 8. Okay, so here only the vertices with the finite key values will be shown, and here it will be marked as green. Okay, so next one, what you have to do, pick the vertex with the minimum key value. So from adjacent to 0, which is already included, 1 is having minimum. This is not included in the minimum spanning tree set event. Okay, so you are going to include 1 and you mark this as green. Okay, so 0 1, and similarly update the key values of the adjacent vertices. Okay, so this one will have 8 and then 8. Okay, so 0 1 are already included. So next one, what you have to do, okay, adjacent to this one, pick the vertex, okay, with the minimum key value. Okay, so here if you can see 1, that is 2, 0, that is 7. So you can either pick 2 or maybe 7. Okay, so here maybe you can pick 7. Maybe you can pick 7. You can also pick 2, but you can also pick 7 even. Okay, so 0 1 and 7, and you try to update the key values of the adjacent. So adjacent means, so here corresponding to 7 you will have 8 and then 6. So you are going to update it. Okay, then you have to pick the vertex, okay, with the minimum key value, okay, and not included in the set. Okay, so adjacent to 7 you have 6. Okay, so 6 is actually included already. 0 1 7 is there, 6 is already included. Okay, so the adjacent values, okay, 5 and then 8 are updated with the values, the key values are being updated. Okay, so you try to do all this one. Okay, so everything will become green even. Okay, so this is how you'll try to get the following graph. The advantage is that like disjoint sets even are connected by using the spanning tree. So this is the Python program, okay, especially for the Prim's minimum spanning tree algorithm, and especially it's for the adjacent matrix representation. Okay, so you import the system class graph, you define the initialization, the vertices. Okay, so self.v vertices. So self.graph, okay, will have 0 for column in the range of vertices, for row in the range of vertices. Okay, then you have the utility function for constructing the minimum spanning tree stored in the parent. Okay, so define print minimum spanning tree self parent. You have the edge, okay, the weighting factors. Then you will have the loop for I in the range 1 comma self.v, then parent of I. Okay, so that you will be printing self.graph of I, parent of I. Then similarly you have the utility function, okay, to find the vertex with the minimum distance value. So define minimum key self key and then MST set. Okay, then you pick up the minimum distance vertex from the set of vertex which is not processed. So first of all you are trying to include, then you are including the minimum value, so that you are going to have. Okay, so that is the reason u is equal to self dot minimum key comma MST set. Okay, then you put the minimum distance vertex. Okay, so MST set of u equal to true, then you will go with the for v in the range self dot v. If self.graph uv is greater than 0, and maybe the set would be equal to false, which means that it's not included. Okay, so and afterwards the key is greater than the self.g, then you will have the key of vertices, okay, which is equal to self dot graph of uv, which means that it is included. Next one. Okay, then the parent of v, it is updated to the u. Okay, then you will go with the print mst of parent. So this is the driver code. Okay, so if the name is equal to main, okay, the g will have the graph of 5. So here you will be having 0 2 0 6 0 203 will actually update the vertices, I mean the weighting factor corresponding to each of the nodes. Okay, so that you will be establishing is a matrix. Okay, so similarly if you can see this one, it's having 2. Okay, and this one it's having 3, it's already repeated. Okay, 3, this one it's having 6, and this one it's having 5. So that's how you'll categorize the weighting factor corresponding to the edges.